All right, hello everybody. Here's our notes on Unit 6.5, talking about energy of phase changes. Going to go through, talk about what we're learning, do a few of the problems together, then leave some you-dos for you at the end if you want to try some out. So, what's our big thing we're learning about today is the two effects of our heat energy. Heat energy can increase the kinetic energy. Different ways that we can have kinetic energy are translational, vibrational, or rotational energy, which increases the average speed and increases temperature. This is governed by the specific heat capacity and can be calculated using our heat equation that we've worked with previously. That's the Q equals mc delta T equation. We also can use heat energy to break intermolecular bonds, which moves our particles further apart. That has no effect on the average speed and no effect on the temperature. This people call latent heat because we see no temperature change associated with that heat. So we've talked about the increase in kinetic energy one, working with the heat equation. This other one, the breaking of intermolecular bonds, is how we do phase changes. So, when heat is released or absorbed during a phase change, we don't see a change in temperature. You can see that on our graph here when you look in this area. Here, I'll do that in a better color. In this area here or in this area here. Notice there's no temperature increase. The temperature stays constant while the phase change is happening. So previously, when we've looked at changes in kinetic energy, we would be looking somewhere like on this hill here, changing from 20 degrees Celsius up to 80 degrees Celsius. And we're looking at that change over that range. We're adding heat. We're changing the temperature of, in this case, water, if we're looking at this liquid and we're calling it water. So in this example, we are seeing that change in phase. I'm sorry, not the change in phase, change in kinetic energy, changing the temperature. When we change phases, though, we see that the temperature gets held constant. So that's that latent heat. That's where the heat is being added, making the phase change happen, but doesn't change the temperature of our overall system. Those are those plateaus that we see. We see that the segment for the boiling section is longer than the segment for melting because separating liquid particles to form a gas takes much more energy than to get from solid to liquid. Right, we see this, so we've talked about this with intermolecular forces way back in Unit 3, right? Getting it from vibrating as a solid to flowing past each other as a liquid doesn't take that much energy because they're still relatively close together. When we turn into a gas, we completely separate those intermolecular forces. It takes a lot more kinetic energy to make that happen, and so we have a longer stretch of boiling that occurs because of that. Now, there's a new heat equation we're going to be talking about here. This one is one that you use just for phase changes. So specifically, this part here is only when we are performing a phase change. The other equation, the Q equals mc delta T equation that we've learned previously, that one is for when we're not doing phase changes. We're heating up or we're cooling down. Here, when we're talking about doing a phase change, our equation is either Q equals m delta H or it's Q equals n delta H. M for mass or N for moles. It just depends on what unit we're given to which of these two equations we use. They're basically the same thing. It just depends on what we're looking at for our given information. Looking at how do we use that, right? Calculating heat for our phase changes. In these problems, the two we're going to look at, notice that we have our delta H is in joules per gram, joules per gram. Because we're working with grams and joules per gram, here we're using the Q equals m delta H because we're looking at mass. If they gave you moles, or it was a joules per mole for the enthalpy, then we would instead be using the N delta H because we'd be working with moles instead. So just make sure your units agree. In these problems, we're going to be talking about grams for everything. We have mass of water, we have grams of ice, and joules per gram. So everything here is going to be the M delta H. So our equation we're using, Q equals m delta H. Let's start trying to use it, and let's see what kinds of answers we can get. First up, number one, we are calculating the amount of heat required to melt that ice. Heat is Q, that's what we're solving for. How much ice do we have? Well, we have 0.500 grams of ice, that's the mass. And the delta H is 334 joules per gram. What happens when we do this? Grams cancels grams, and our answer for Q ends up in units of joules for energy. That makes sense. When we plug our answers in here and we do our 0.5 times 334, I get that this should take 167 joules of energy to melt a half a gram of ice. Now for number two, we have a different type of problem. It says calculate the mass of water that can be boiled if I know how much energy I'm using. This 564 joules, that is the Q, and then I have my delta H. So I've got 564 joules is equal to the mass that we don't know times my delta H, which is 2256 joules per gram. Now to solve for the mass, I need to divide both sides by the 2256. Canceling my joules and leaving me with a unit of just grams. Here it's going to give us 0.250 grams. So two different types of problems that we can see here of working with our phase changes is to calculate how much heat is needed to melt or to boil or to freeze or to whatever the phase change is, how much energy or heat is required to do the phase change if we know how much there is, or if we know how much energy we have, what is the mass that we could melt or boil or freeze or whatever phase change we're talking about. Now, looking back, when do we see problems that don't use this same thing, right? Notice here on these problems for 3 and 4, we notice that we have a C again, that specific heat. We have that C value, and this we see a temperature range as well, right? I am heating or I'm cooling something, I have a change in temperature. When I see that I have that change in temperature, remember that is the Q equals mc delta T equation that we've learned about, right? Change in temperature gives us delta T. C is that heat capacity. When I see those kinds of things in my problem, I know that I'm working with that equation instead. So when do we use which form of Q? It depends on if we're at a phase change, like we were in numbers 1 and 2, where you see we've got that heat of vaporization, that heat of fusion. We see the enthalpy, how much energy is needed to do a phase change. Here, we're just talking about we're heating something, we're cooling something. So for number 3, the amount of energy required to heat this water, right? Amount of energy to heat 25.0 grams. My specific heat is 4.18 joules per gram degrees Celsius. And then my delta T, I do 80 minus 20 degrees C, right? And that's going to cancel degrees C, leave me with just joules. My delta T over there is going to be 60 when I do 80 minus 20. So I'm going to do 60 times my specific heat times my grams gives me a total of 6,270 joules, which we could also write if we wanted to as 6.27 kilojoules. Remember, kilojoules is 1,000 joules. So because we had 6,000 joules, we could write that in kilojoules if we wanted to. That's how much energy is needed to heat that water up 60 degrees. Now our other one, what mass of ice is required, or what mass of ice would require 130 joules of heat, right? That 130 joules is my Q, my amount of heat. I don't know the mass. We're going to solve for that. Our specific heat, 2.09 joules per gram degree C. And my delta T here, I'm trying to go from -10 to -40 minus -40. My delta T here is 30. To solve for M, I'm going to do 130 joules divided by the 2.09 times 30 for my delta T, and that's going to give me my mass, right? To solve, I divide to get rid of the stuff by there. When I do that, I get a total of 2.07 grams. So with 130 joules, I could change 2.07 grams of ice from -40 up to -10 degrees Celsius. So a big thing I want to talk about, this was kind of just a review of what we've talked about with that heat equation. But the big thing is for these ones, we're talking about a phase change. We use the Q equals M delta H. For these ones, we're not talking about a phase change. We're doing Q equals MC delta T like we've done before. For some ones for you to try out, here's kind of a heating curve for mercury, so you can use that to calculate the heat needed to freeze 100 grams of mercury, and you can get your delta H values off of the graph there. You can try that one. How do we use the Q equals M delta H equation? The one thing I want you to pay attention to and make sure that you notice is this is in grams, this is in kilojoules per mole. Kilojoules per mole. So make sure you pay attention to the units on those and make sure that your units agree when you do your math. The other problem that you're going to do is here, taking aluminum, melts or freezes at that 933 Kelvin, how much energy is required for you to freeze 2.5 moles of aluminum, given your values for your delta H of fusion and delta H of vaporization. You got to pick the right one, and then you're going to solve for how much energy is required to freeze 2.5 moles. So that is our unit 6.5. Thank you guys for watching. Hopefully you guys are doing well, and I will talk to you again soon.